All right, so design energy targets for plant maintenance projects. Kaiser now has design energy targets for work in existing buildings. I believe we may be the first owner to have them, and so this should be fun. Our design requirement is for the engineer of record to evaluate the design energy use against these targets and develop plans to meet the targets. The way this is stated does not say that you always need to meet these energy targets in every building, but we always need to assess where we stand relative to these targets and know what it would take to get them. The good news about these energy targets is that we know that they are feasible. Because they come from our existing portfolio. Each of these targets comes from some very real examples in our higher performance buildings and our higher performance systems. So we know that they are possible. It's just designing to them that becomes our challenge. Now, the easiest way to look at these energy targets is with an energy model. And of course, I'll stop right there and say that most of our plant maintenance project work, our design engineers do not develop an energy model. But if you do, the process is relatively simple. Every load or energy modeling software, including Trace, can output an 8,760 line output. You simply take those results and sort them into fan power and cooling power and heating power and block them out by outside air temperature. And then we can report what's the fan power at 55 degrees, what's the cooling power at 75 degrees, what's the heating power at 65 degrees, and just simply list those in our basis of design relative to the targets. But even if you do that, even if you have an energy model and you do the energy model, you still have to look at the equipment schedules and make sure the equipment can meet those energy targets. And so let's take a look at some examples. In this example, this is for cooling. We have a 17,000 square foot project, and our cooling coil has 700,000 BTU of sensible and 1 million BTU of total. That's 12.7 to 18.1 watts per square foot. Our target cooling energy at 85 degrees is 2.2 watts per square foot, so that's significantly less. Our target cooling energy at 75 degrees is 1.6 watts per square foot, which is getting down below 10% of the coil capacity. So this tells us something. If the coil capacity that we've selected on the plans is vastly more than our 85-degree energy target, then it's very, very likely that either the design doesn't meet the energy targets or that coil operation is going to be unstable in those shoulder conditions. So even if our energy model says that we meet the target, we need to make sure that we have a viable equipment selection for that solution. In this case, is this valve going to be fluttering, right? Or is this coil going to be producing a 2-degree or 4-degree delta T throughout that shoulder season? Another example, let's look at heating. Same project, this is 17,000 square foot. And for heating, what we can do is we can sum up the zone minimum CFMs. We've come to call that number the sum of the minimums. If it's a constant volume system like this one is, the sum of the minimums is the sum of the zones. If it's a variable volume system, then the sum of the minimums is the sum of the minimums. And a way that we can calculate the reheat is to assume neutralization of the air at the sum of the minimums. So if it's 75 degrees outside and we have no setbacks, then we'd be cooling all of that supply air down to 50 degrees. And in the worst case scenario, we're going to have to reheat it back up to 75 degrees to neutralize it. Well, that's 8.5 BTU per square foot. Now, if we do have a supply air setback, then we're going to take that minimum air down to 60 degrees, and then we're going to have to reheat it back up to 75 degrees to neutralize it. That's 4 BTU per square foot. Our heating target is 1 BTU per square foot. So in either case here, we're falling well outside of that energy budget. Well, what if this were a VAV system? Then the sum of the zone minimums could be quite a bit less. It could be as low as 0.45 CFM per square foot. And in that condition, without a setback, we'd be at 2.5 BTU per square foot. But if we did have setbacks, then we'd be down at 0.7 BTU per square foot and soundly under our heating budget. Here's an example looking at fan power. Our fan power is 75 degrees is 0.3 watts a square foot, and our fan power target at 85 degrees is 0.4 watts a square foot. 17,000 square foot project, 25,000 CFM of air. There are 6 supply motors and 3 return motors, so the grand total brake horsepower is 1.9 watts per square foot. So this is over our target, and it's over by a factor of 5 or 6. But again, what if this were a VAV system? Then we would be looking at that sum of minimums. 6,800 CFM, that fan power would drop off significantly. There's a couple ways to calculate that. You can use the fan laws. There's one example there. The fan laws are incorrect because they don't assume the pressure set point. So we could do the math at 2 inches of pressure, and either way, we'd get down to this 0.1 watt per square foot, which is soundly below the energy target. But again, that brings us back to the idea of viability. If the sum of the minimums is 6,800 CFM, is this air handler capable of operating at 6,800 CFM? What would it be doing at 6,800 CFM? This is a fan wall, so there should be a sequence that can get us down there, but we want to see a selection from the AHU vendor with some fan curves that actually show that those fans are stable at the operating points that they need to be in along the way. This viability check has dinged us. It's particularly important in DX units. We have DX units where the manufacturer puts in place a maximum turn down to 50%. So a 25,000 CFM unit is not able to turn down below 12,000 CFM. So those definitely need to be checked at the time that you're scheduling. Last example here is to look at a boiler system. In this case, we have a 220,000 square foot project, and we have 3 boilers that are 25 million BTU each. So if we're running all 3 boilers, we'd be at 33 BTU a square foot. If we run 2 boilers, we're at 22. If we run 1 boiler, we're at 11. Our heating target at 75 degrees is 1 BTU per square foot, which is 9% of one of these boilers. So unless that boiler is capable of doing better than a 10-to-1 turn down, then this boiler system will never be capable of operating down at our energy target level. That's problematic. Even if we have a system that has a higher demand than that right now, we want to make sure that we have equipment that can operate at our energy targets. So to sum up here, we now have published energy targets that work in the existing buildings. So a couple of Q&A points on this. The targets are for both medical office buildings and hospitals. Hospitals do not have separate or higher targets. The medical office buildings should meet these targets fairly easily. These targets apply to all of our buildings regardless of climate. So if you're doing a building in a climate that gets to 110 degrees, you'll notice that we don't have a target for 110 degrees. What we're doing is we're checking the energy of that building when it's 75 degrees and when it's 80 degrees, right? The target's not at the max, the target is at the common positions. Not all of our projects are going to meet these targets. What happens if I don't meet the target? What if my building can't do these? Well, that's okay. The way this requirement works is that our basis of design needs to have a write-up comparing the project work to the energy targets, so we know where we're at. We identify the path that it would take to get to these targets. If the only option to get to the targets costs $100 million, we're probably not going to execute that, but we will always know where we're at relative to these targets and what the path is to get there. So that's the close of this section, and so I will remind you again to put any questions you have about this concept into the chat box.
When talking about an hourly energy target, are you talking about an average hourly energy target or expected hourly energy based on varying loads?
I think that's a great question because oftentimes we get 15-minute interval data and or 5-minute interval data. And so that would be the hourly usage in that hour. So the way that any calculation that we can do, we use units of BTU per hour is very typical, and we look at 8,760 hours a year. So we'd be looking at 10 horsepower in that hour. So the horsepower may actually fluctuate up and down in that hour on 5-minute basis, and so we would be looking at the average.
No energy targets above 85 or below 55 Fahrenheit.
Yeah, so what we tried to do there, for years and years and years, I've been struggling with how do you set energy targets for existing buildings because they exist in different climates, right? How do I set an energy target for San Diego and Fontana and Seattle? They exist in different climates. So the way that we finally did it was to think about the fact that each one of those buildings has hours when it's at 55 degrees, for example. Whether you're in San Diego or Fontana or Seattle or Baltimore, there are hours when that building is at 55 degrees or when the weather is 55 degrees. So during those hours when you're at 55 degrees, you should have comparable energy performance among those buildings. And so that's where the energy targets come from, right? Is at 55 degrees, we should be, an efficient building should be performing with this amount of energy, per square foot in these different systems. At 75 degrees, which is what we kind of think of as the neutral condition, each of those climates has hours where you're at 75 degrees. And so we want to make sure that we can benchmark the performance of the different climates at 75 degrees. That's sort of the origin there. It kind of did take me 10 years of just scratching my head to figure out how to publish energy targets. We'll see how this works. If you have better ideas, please let me know.
Do the energy targets calculate include building process loads like IT loads, etc.?
Great question, and not there is not an energy target for plug loads. The energy targets are for the buckets: cooling loads, fan loads, and heating loads. There's not actually an energy target in place for lighting loads that we publish. So those buckets are going to happen, and each one of those will have an effect on that cooling load bucket, but we're not specifically sort of targeting a certain level of plug loads or a certain level of lighting loads. I hope that answers the question.
Do the energy targets posted today are for recirculating systems, not 100% outside air systems OA? Will there be energy targets for 100% OA systems?
That's a good question, and they are not. They're not differentiated. So they're not separate targets for 100% outside air systems and recirculated air systems. The good news I can tell you, like the heating target and the cooling target, is that we've seen that level of energy performance in the 100% outside air systems. So that's kind of the weird thing about the energy targets, is that we do know that these are possible. We've seen them. They come from our buildings, and most Kaiser hospitals. I don't know who asked the question, but you probably know that most of the hospitals that we have in our portfolio are 100% outside air. So anytime we're looking at historical data, that's what we're seeing. So I think where the question was going is, should we have higher energy budgets for 100% outside air systems? And the answer I would give you is no.